Welcome to Spring LIB.
In this exercise, we're going to be talking about circular motion, and we also going to need the concept of radius of curvature. So let's first explain these concepts before actually solving the exercise. So when we're talking about circular motion, we're talking about a particle whose trajectory is a circle, and at any point in the trajectory, the acceleration of the particle can be decomposed into two components. One of them is the centripetal acceleration, that points towards the center of rotation, and the other one is the tangential acceleration. The centripetal acceleration exists even if the speed of the particle doesn't change and accounts for the change in direction of the velocity. And it's equal to v squared over r. V is the speed of the particle, r is the radius of curvature. The tangential acceleration, on the other hand, accounts for the change in speed of the particle and is equal to dv dt. Now, given a certain curve, an arbitrary curve, okay, such that we have the expression for y as a function of x, we can find the radius of curvature of the curve in any point to be equal to 1 plus the derivative of y with respect to x squared to the 3 halves divided by the magnitude of d2y dx2. Okay, and we're going to use these two concepts in our exercise. So what we have is a car that is moving along a hill that is shaped like this parabola here. Y equals 20 times 1 minus x squared over 6,400. And the mass of the car is 0.8 megagrams, which is the same as 800 kilograms. And our goal is to find when x is equal to 80 feet, here in the figure, and the car has a constant acceleration of 9 meters per second, what is the normal force that the surface exerts on the car, and what is the friction force that the road exerts on the wheels of the car. In order to solve this, we're going to need to decompose, to draw the free body diagram on the car. So this here is the car. Now we need to draw the free body diagram. What we have is the normal force that points in this direction. We also have the gravitational force pointing downwards, and we have the friction force that points opposite to the direction of motion. Now I'm gonna define an angle theta, this angle here, that the normal does with the vertical. It's the same angle as the friction force does with the horizontal. Okay, and I'm briefly soon going to find what this angle actually is. But before I do that, I'm going to decompose this force into a component along the r direction, and the r direction is the centripetal direction, so this direction here, and another component along the tangential direction. So notice that the normal force is along the r direction, while the friction force is along the theta direction. So what we really need to do is to find the components of the gravitational force. Okay, so in the r direction, we have that the gravitational force is equal, and actually, let me write the r direction in the opposite direction. So r must be pointing towards the center of rotation and not the opposite. Okay, so now it's correct. So along the r direction, we have mg times the sine of theta, I'm sorry, actually the cosine of theta, minus the normal, and this is equal to m times the centripetal acceleration, which, as I said before, is v squared over r. Theta is mg sine of theta minus f, which is the frictional force, and this is equal to m times the tangential acceleration. Okay? So let's leave this here. We're going to use this. But now let's talk about both the radius of curvature, which we're going to use here, and also theta. So the radius of curvature, and we want to know the radius when x is equal to 80. So I'm going to use the formula that I wrote before in order to find the radius of curvature. Now, in order to find r, we also need to find dx, dy dx, and d2y dx2. So dy dx is equal to minus 2 times 20 divided by 6400 times x. So this is equal to minus 0.00625x, while the 2y dx2 is equal to minus 0.00625. So we want to find r when x is equal to 80 meters. So in order to do that, we have 1 plus minus 0.00625 times 80 squared to the 3 halves divided by 0.00625. So r is equal to 223.6 meters. This is the radius of curvature. Also, we're going to need to find what theta is. So notice that we have this parabola here. And theta, I define theta to be this angle here. Okay. Now notice that this theta is the same as this theta here. And theta can be found to be such that the tangent of theta is equal to minus the derivative of y with respect to x. And the minus is here because actually there is a change in convention. Okay, usually theta here will give us, if we calculate theta to be just the tangent of theta equals the derivative of y with respect to x, we're going to have a minus sign because the function is decreasing. We don't want that, so I'm just putting this minus sign here. So theta is the arc tangent of minus dy dx when x is equal to 80. So theta must be the arc tangent of 0.00625 times 80 meters. So theta is 26.6 degrees. Okay, so now we have all the information we need in order to solve the equations that we had before for the friction force and the normal force. So I'm going to take the second equation first, the equation for the theta coordinate. Notice that I said before that the speed is constant, meaning that the tangential acceleration must be equal to 0. So this term here is just 0. So I have that the friction force is equal to mg times the sine of theta. Now m is 800 kilograms, g is 9.8 meters per second squared. I have to multiply it by the sine of 26.6. So the friction force is equal to 3.51 kilonewtons. Okay, this is the first answer, and then we have to find the normal force. I'm going to take the first equation now. So I have that N is equal to M G cosine theta minus V squared over R. Now M is 800 kilograms. Then we have to multiply it by 9.8 meters per second squared times the cosine of 26.6 minus V squared divided by R, and R is the value that we found before. It's 223.6 meters. So 223.6 meters. So the normal force is 6.72 kilonewtons. And this concludes the exercise.